Let's look at the error for Simpson's rule. Remember, we talked about what type of error bound we would have with the trapezoidal rule. We want the similar theorem for Simpson's rule. So when we use the nth order Simpson approximation to actually approximate a definite integral, we have an upper bound on the error. And you can see here that this looks similar to that for the trapezoidal rule. We have b minus a, the length of the interval, raised to the fifth power, divided by 180 times e to the fourth, times the maximum on the interval of the fourth order derivative. And as I've noted here, error using Simpson's rule. So one of the examples we used was the natural log of 2, which is represented by the integral 1 over x from 1 to 2. That's what we will talk about with the natural log. Now, what we did was to determine the number of subdivisions for error of less than 10 to the negative fourth, or 1 over 10,000. So when we look here, we see we need to go 2 orders higher on the derivative. So at this point, this is where we stopped with the trapezoidal rule. 2 times x to the negative 3. So let's take one more derivative to get negative 6x to the negative fourth, and then one more, the negatives will absorb and we get 24x to the negative fifth. Now we can fill in this upper bound with all the parameters. 2 minus 1 to the fifth power divided by 180 times e to the fourth, and then we want the maximum of the absolute value of the fourth order derivative. Now, just like before, this is a decreasing function, so we can maximize it at the endpoint. Now, depending on the function you're working with, you may have to work a little bit harder to come up with an upper bound, but here we can easily get one. And that would clearly be at 1, so that'll give us a 24. And so now what we do, we factor the 24, 2 times 12, and the 180, 2 times 15. The 12's absorbed, and we get 2 over 15 times e to the fourth, and we want that to be less than 1 over 10,000, as we've written here. And so now we can divide out the 5's, so we get 2 divided by 3 e to the fourth less than 2,000. Then we can reciprocate 3 e to the fourth divided by 2 greater than 2,000, and then solve for the e to the fourth by multiplication by 2/3. That will give us e to the fourth is greater than 4,000 over 3. But then, of course, by the cube root, we can get a value for n. This will be the cube root of 4,000 over 3, which is approximately 6.04. And so what we want to do is go to the next greatest integer for our estimation process. Now, for Simpson's rule, we do have one rule or one item that differs from the trapezoidal rule. Because we use quadratic functions in our approximation, we need 2 subintervals for each approximation. And so we require the even number of subdivisions here. If you look in your notes, there's a very elegant derivation of this rule. So please look at that and note that we always need even for this to work. So we will take n equal to 8. So therefore, we take the length of the interval, which is 1, and divide by 8 to get our nice regular partition. So all the subintervals have this length. And so we can easily write a partition. We start with 1, then add 1/8 and 1/8. So we have 9/8, 10/8, 11/8, etc., 14/8, 15/8 to 2. So this will generate 9 elements in the partition, which gives us the 8 subintervals. And I've written here reasonable, very, very reasonable. So what's nice about Simpson's rule is that it provides second order convergence, which exceeds that for the trapezoidal rule. And so this is a very, very efficient method for approximating integrals, which is used widely in computing environments, and certainly for those fancy calculators that are the rage these days. And we are done.